So, good afternoon, everybody, and welcome to this other BrIAS Seminar Thursday. Also, today we have a very nice program, and actually, it's my pleasure to invite our first speaker of the day, that is Professor Pierre Lambert. Please, Pierre, come. So, Pierre Lambert is a professor of this university, of the ULB, who works in mechanics and robotics, in particular in the small scale. Pierre is also one of the vice deans of our faculty. In particular, is the vice dean that works on international relationships, which is, I think, very relevant for us here at BrIAS. So we are also very happy to have you here for institutional reasons, not only for the scientific one, but actually I'm much more interested in the scientific one, as you know, than the institutional one. So I'm very eager to hear about your talk. So I leave you without further delay you the microphone, and I'm very curious about what you will have to say.
Thank you, Emanuele. So good afternoon, everyone. I'm in the field of microrobotics, which I usually define as robotics. So it means motion at small scale. So motion can be done, for instance, with non-conventional ways that you can see on the right movie. These are three floating parts at the surface of a water bath, and the components are driven by thermocapillary flow induced by the red point that you see on the screen, which is a laser. So that's a way to produce motion on a non-conventional way. I will also speak about compliance and smart material. Here you have a shape memory polymer, which can deploy into the logo of my department when you put when you put heat on this material, which has been previously educated. And the third keyword in my title, I don't have the movie here, but you can have a watch on YouTube later on. It's the World Guinness smallest stop motion movie with a character here, which is a tribute to David Bowie. And the character is 300 micrometer tall, which means that the figure that you see here, this is more or less 50 micrometer. And we have produced hundreds of these figurines, and they were imaged to make a stop motion movie. So we will also speak about small scale. So the first topic I would like to discuss with you is what we have called active voxels. I will explain in a couple of minutes the topic. So it's a joint project with ULB and Université de Mons. And it is inspired from the well-known pneumatic soft robotics. You all know about balloon. So this is the children balloon in red for parties. And then you have other kinds of balloon or pneumatic actuators. With the red balloon, you have isotropy, which means that more or less when the child is inflating the balloon is expanding isotropically. But you can introduce anisotropy in the balloons or in the pneumatic actuators by injecting some anisotropic constraints. So for instance, here you have circumference of black wires constraining the radial expansion of the balloon and so promoting the axial elongation of the balloon. You have the opposite, which is known now for decades, and this is the principle of the Machiben muscle, which is also a balloon in which you apply a pressure, but the pressure is turned into a contraction. And then you have all the bending balloons, all the bending pneumatic actuators, where you put some constraint on the intrado of the structure, so it cannot elongate on the bottom side, it can only elongate on the top side, and as a result you get bending. So the idea was, or the initial observation was that we can consider three elements in these actuators. There is the isotropy or the anisotropy of the stimulus. In my pneumatic balloon, I consider the stimulus to be the pressure. Pressure is anisotropic, but you could have polarized light, which is an anisotropic stimulus. Then you need a transducer to convert the stimulus into a motion. In this case, this is the air of the balloon. The air is also an isotropic medium, but you could have structured materials that have a privileged direction, and which introduce the anisotropy. And if you do not have anisotropy on the stimulus and on the transducer, you can think of adding some anisotropy by putting reinforcement links on your balloons. So in the top figure, in the red balloon, there is absolutely normally no anisotropy, and so it results into an isotropic motion, while in the Machiben muscle, or derived version of it, you have anisotropic constraints. So based on this, we wanted to print, not to use air pressured actuator anymore, but to 3D print actuators based on this idea. And first, we wanted to understand how we have to put the constraints to be able to tailor any of the degrees of freedom. And the first trials were made with paper, and we made paper cuts in the paper wrapping. So here you have in black, in white, sorry, the paper wrappings, and you can see on the paper some cuts allowing or constraining some motion, and as a consequence you can create bending, compression, elongation, or twisting. So this is at the centimetric scale with an inflatable balloon. So this was just the first step. Then we first got rid of the air pressure by using another medium, another transducer, which is an elastomeric matrix containing ethanol bubbles. This is inspired by the work of Aslan Miriev. When you heat this mixture, the ethanol bubble inflates, and as a result, you have an isotropic expansion of the mixture. And we again constrained this mixture by wrapping it in sheets of paper, wrapped by cubes actually, with the 6 faces of the cube. We all played that game when we were kids. And the red line on the different phases indicates the presence of cuts in the paper. So perpendicular to the cuts, the paper are allowed to move, but not in the direction of the cuts. And by doing this also at the centimetric scale, we were able to get bending, twist, shear, contraction, and elongation. So this confirmed the possibility to constrain any cube, any voxel of active matter to produce any motion. And now we arrive at the interesting step, which is to use a smart material which can be printed. And this smart material is an hydrogel. And an hydrogel, this is a polymeric network able to drain water or to expose water, so to be a bit hydrophilic or hydrophobic according to the temperature. So if you use the temperature as the stimulus, you can drive the shape or the volume of your hydrogel. So it's a contractive material, not an expanding one, a contractive one, but more or less an isotropic contracting material. And so you mix all the constituents of this hydrogel, and then we polymerize it with the machine, with the 3D printing machine that we used to print David Bowie. But now we use it to print the hydrogel. And we were able to make cubes of hydrogel with a scale of a size of 50 micrometers. So if you look at the actuation strain, so the linear strain, you can consider the strain as a volumetric expansion, but also the linear strain along in direction. You see that this linear strain, which is negative because it's basically a contraction, this contraction is increasing with the temperature. And that's the effect that we wanted to use as a stimulus. And what we also observed or wanted is to show that according to the laser power during the polymerization, you can tune the stiffness of the polymeric network. If you put more energy, you will result in more polymerization and in more stiff structure of the polymer. And what we made of this information is to make gradient of energies in printing our hydrogel. So the red phase here is just the polymerization of the hydrogel that we get at a low energy level. And then with the same machine, without any manipulation, we reuse the same laser to put an extra dose of energy in the light blue areas of our voxel. And so the light blue, the cyan parts are more stiff and can act as reinforcement links against the contraction of the red part, which is the active hydrogel. And again, this is the isotropic cube. This is a bimorph. This is a bending structure. This will serve as a compression structure. Here we have the twisting structure, and here we have the shear structure. So we printed this. You can see here on the top right 4 of these voxels having more or less an edge of 40-50 micrometer, and we printed many of them connected to a glass sheet, a sheet of glass that was immersed here in the center of the setup in a bath of liquid, which is sketched here below. And so we were able to image the motions or the displacements of this voxel according to the temperature of the water bath. And so according to the temperature here, you have different snapshots done at different temperature. You see first the general contraction effect, which is due to the general contraction of the hydrogel. And you can also see an important bending. We can get more or less 20 degrees out of a structure with a length scale of 50 micrometers. And that results in a very important curvature and very relevant curvature for application where you do not have a lot of space to create motion, such as the exploration of the endoscopic natural pathways of the human body. So this is for the bending. Here you have the compression. Here you have the twisting. So you observe that you get more or less the same order of magnitude in terms of angular deviation. And so that's what we could realize. So these are successive snapshots of different structure. So now what we would like to do is to make first printing these actuators at the extremity of an optical fiber, not on a glass slide anymore, but on a fiber. For this, surprisingly, we are targeting larger voxels, so our challenge is not to further downscale our system, but rather to upscale it, and we have to solve some technical problems for that. And then we would like, and this is the second idea, we would like to stack successively 2 or many of these voxels and to shape them to be selectively habituable according to a stimulus that could still be the heat, but not the heat provided by a humid or a liquid environment, but the heat obtained by the conversion of light. So we want to use the optical fiber to send light power on these voxels, and according to the wavelengths of the light, we could selectively actuate a certain numbers of degrees of freedom. And such a system would have all the requirements to fit the size and the requirements for endoscopy in the human body. Not for the gastrointestinal endoscopy, rather for the ear, nose, throat environment or the lungs environment. And this is a new project that we have just started. The second topic I would like to discuss with you is not based on smart materials, so we will not discuss about active matter anymore. But we will still use the elasticity of the material to create motion. And this is a project that we have with Université de Liège, with Christophe Colette in the precision mechanics department, and with Christophe Kochter in Mons in the photonics department. So what we would like to do is first to produce compliant mechanisms, such as the one that I showed you before the speech, compliant mechanism, not 3D printed in plastic, but 3D printed or 3D shaped in glass. Because glass, I will show you that in a couple of minutes or seconds, glass is an extremely good candidate to make elastic structures. On top of this, glass is very interesting because it's the substrate of all the photonic knowledge, and so we will try to introduce optical fibers in our glass 3D structures, and we will guide the light inserted from an optical fiber in the mechanism. We will guide the light in the mechanism thanks to waveguides, and we pattern Bragg gratings along these waveguides. So I will show you that the Bragg grating is basically a technique with which you can measure the strain of a structure. And so we are building strain sensors of glass-based compliant mechanisms. So we are producing kind of strain gauge, but everything is in glass. There is no electrical part. And that's with the idea to put that at the extremity of endoscopic catheter to be able to measure efforts that are applied in the human body during some operation. So we, of course, don't think about glass initially or directly when we are speaking about elastic material. That's because due to the usual thickness of glass that we have in the windows that we are seeing or handling on a daily basis, the thickness are so high that we get the feeling of a very fragile and brittle material, and that's true. Metals are plastic materials that can deform permanently beyond the elastic range, while glass is a brittle material which will break beyond the elastic range. But within the elastic range, glass is much better elastic material than most of the materials. On this map, what you see is the plot of typical materials used in microfabrication, like resins here in blue, operated with the high-resolution 3D printer that I discussed. Glass is located here. Silicon, which is well known from the silicon microfabrication techniques, which is used in the MEMS industry. And then you have a variety of red metallic symbols indicating steel, titanium, copper, beryllium, and invar. The first axis here is an elastic range coefficient, so which describes to which extent this material and the associated geometry that you can shape thanks to the technology available for this material. So you cannot compare the elastic properties of plastic, which is 3D printed, with the elastic property of silicon, which is shaped in the microfabrication clean room. So you have to take into account the material property, sigma over Young modulus, this is a measure of the elastic deformation that you can get, and an aspect ratio which comes from the limits of the associated fabrication techniques. So you already see that on that axis, glass is actually the second better material, just after the copper beryllium, which is well known for its use in elastic structures. And the second axis is a kind of stiffness coefficient, which is proportional to the Young modulus of the material and the cube of the thickness of the associated element. And the thickness H here is also depending on the technique that you use to shape the material. So you see that from that first diagram that glass is an interesting material. Moreover, you do not have any thermal expansion or very limited thermal expansion, so it's rather insensitive to temperature changes. It's obviously optically transparent. You have a very low internal damping when you use glass as an hinge in the vibration domain. And glass can also be the substrate of any biological process which already exists to be used on glass. So we use very basic glass, and this is fused silica glass slides produced by Sigurd Wafer. So microscope glass slides with a conventional Young modulus of 72 gigapascal. This is close to aluminum. with a material strength that we measured based on structure that we broke, and we estimate the maximal elastic stress to 1 or 2 gigapascal. And we are producing an annealing test, but I don't have results yet to present. This idea to instrument glass with photonic structure is not new. It has already been reported to measure the deformation of a glass plate. But it's just a plate, it's not really a mechanism, what I would call a mechanism. The emergence of glass-based compliant mechanisms is quite new. It's less than, or I would say 10 years ago, thanks to the development done by Yves Bellouard, which is now professor at EPFL, and before it was in Eindhoven. And Yves Bellouard led a European project called femtoprint to use a femtolaser technique to shape glass at the small scale. And so you see the kind of elements that you can obtain. You can recover cross bars, which are the cross pivots that I let you handle before the beginning of this speech. So this is exactly this idea, but at a smaller scale in glass. And on the, I don't have a notch edge with me, but so here you have just a thin part of glass, and you see that you can bend it up to 62 degrees, which can be counterintuitive except for people used to handle optical fibers. If you already handled optical fibers, you know how flexible it is. This is the idea that we are using. So this femtoprint process is based on a two-step manufacturing technique. First, you illuminate the glass with a femtosecond laser. You bring energy, and this energy creates densification of the glass, densification. And this densification corresponds to some contractile stress, and surrounding the zone of densification, you have areas with tensile stress. And this tensile stress region have been observed to promote the etching of the glass in a second step by a strong acid or a strong basis. So we are using a bath of KOH to reveal, to etch the parts which have been illuminated by the laser. So there are a lot of technical parameters, such as the energy that you deposit at each pulse of the laser, the scanning speed of your laser, and you have different regimes. I don't want to enter right now. But so this is the message, the observation done by the early work by Bellouard. At moderated exposure dose, you have this densification of the area illuminated by the laser, surrounded by a tensile stress area, promoting the etching by the KOH or the HF. But if you increase the dose too much, you get an optimum, because beyond this optimum, the tensile stress is so high that you create cracks in the material. And the cracks stops this beneficial effect of etching the glass by the etching agents. So we need to work before the emergence of these cracks. And in the following, we will use low dose just to operate a slight densification of the glass, which also means a slight increase of the refractive index of the glass. And that's how we will be able to produce waveguides, because a waveguide, it's a guide where the refractive index is basically a bit higher than in the surrounding material. This is what you have in the Italian fountains in the summertime, where you can see colored lights guided by the water jets. This is because the water has a refractive index which is larger than the surrounding air refractive index. Then by increasing a little bit the dose of energy that we use during the illumination, we are able to pattern periodic variation of the refractive index along the waveguide, which is the Bragg grating technique. And thirdly and lastly, by increasing still further the energy, we are able to reach the etching regime where we can start shaping the 3D geometry of our materials. So these are the parameters that we used to create our 3D structures. So first we created circular notch hinges, which are figured out here. So it's a thinning of a material part in the shape of an arc of circle. And the minimum thickness of the hinge here is at the order of magnitude of 10 to 50 micrometers. So we were able to create shapes like this, or even series of notch hinge, and that we use to characterize the elastic limit of our material. So we imposed some angular deviation to our structures, and we could measure the maximum deviation for which we could get the breaking of the materials. That's how we could do. Then we start producing cross pivot like this one, used to create a rotation in the material. So you have 3 successive beams, one in the front plane, one which is blurred at the rear side of the image, and this one which is perpendicular to the first 2 ones, which is in the middle plate. On this pivot, we have a thickness down to 10 micrometer. So you can see on the right, on the red background image, the angular deflection that we can get out of this mechanism. And when you let it oscillate, you see the good oscillatory properties of the glass material. So we create a mechanism out of this pivot. The pivot is here. A mechanism where the pivot here is used to guide a needle, indicating the angular deflection that we are able to reach. This is a sample that I will discuss again later on, when I will explain how we measured the angular deviation directly from the photonic properties. We also produced what is called in precision mechanics orthoplanar springs. Orthoplanar, ortho means perpendicular, orthogonal. Orthogonal means perpendicular. So orthoplanar, this is a mechanism able to move perpendicularly to the plane of the mechanism. So this is an orthoplanar spring. The plane of the spring is the reference plane, and the spring is used to move, I will show you on the movie, to move out of the plane. So we have 2 parallel, the first one is here, the second one is there. We have 2 parallel orthogonal springs able to guide the yellow part of this mechanism perfectly in one direction, perpendicular to the plane. And we were able to shape these orthoplanar springs in glass. And here we are pressing against the mechanism. And when we are pulling back the red sphere that you see that the system recovers its initial position. So with this, I showed you that we were able to produce mechanisms in glass. So now the next question is, how can we insert the light coming from an optical fiber to connect our mechanism to the outer world? Due to the small size of the mechanism, we cannot use conventional techniques used in photonics to connect optical fibers. They are too bulky. And so we decided to directly inject it or insert the fibers in the mechanism. So this is a glass plate, a glass slide, which will contain the mechanism. And here we have a series of insertion structures. Each insertion structure is made of 3 successive open box or open pockets connected by thin channels, and we can insert the fiber in the successive channels until the fiber is injected at the extremity of the last cavity. And then in front of the last cavity we will have our waveguide. And at the opposite side, we have a similar system to recover the light and then we can use the conventional photonic system to measure how much light power we could transmit from one side of the glass to the other side of the glass. We were also able to characterize the photonic inscription of our waveguide and of our gratings, which will be used for the Bragg grating, by imaging everything in a digital holographic microscope. This is a microscope which is able to capture not only the intensity of the image, but also the phase, like in holograms. And with that, we can apply interferometric techniques or analysis coming from interferometry to deduce the refractive index modification measured by a variation of the phase of the light which is measured. Because the phase shift is proportional to the optical length, which is the geometrical length multiplied by the refractive index. So with this, we were able to have our mechanism, our waveguides, and some gratings along the waveguide. These Bragg gratings are known for a while. They are used in monitoring the health of civil engineering buildings and bridges. So first you create a periodic variation modulation of the refractive index. This is the Bragg grating. And the distance between two elements is capital lambda. This is one of the key geometrical properties of the waveguide. Now imagine that you apply a force, a stress, an axial stress on this Bragg grating. All the material will stretch a bit with an elastic deformation given by sigma divided by the Young modulus. And as a result, the distance between two elements of the grating will increase a bit. And something that I realized I forgot to tell you is that on a Bragg grating, if you send all the wavelengths, which I tried to figure out on my picture going from the violet to the red, all wavelengths are transmitted, but one which is reflected back and whose value depends on capital lambda of the Bragg grating. Which means that if you have a shift in the Bragg grating distance, you will have a shift in the reflected wavelength. And you can measure this. You can measure the shift between the red and here the orange wavelengths. The colors are not representative of the wavelengths that we are using because we are working in the infrared regime, but I cannot show that on the slide. To measure the bending, it's a bit the similar idea. If you create bending, you know that there is a neutral fiber in the middle which undergoes no stretch, no compression. The upper fibers will be submitted to traction while the lower fibers will be submitted to compression. And so we will have a red shift, so a shift to larger wavelength. Here figured out by the switch between the green and the orange on the fibers which are in traction. And we also have a blue shift, so a shift of the reflected wavelengths towards the blue wavelengths in the zone of compression. So we created waveguides in our compliant mechanisms. So I told you that we were able to make thinning of the materials down to 50 micrometers. And in these 50 micrometers, we put a waveguide. Not exactly on the neutral fiber because we could not measure anything on the neutral fibers, but just a bit below, a bit aside. So the first tests that we made were pure traction uniaxial stresses. So the idea was to create a glass structure with the waveguide and the Bragg grating and to pull on it through an elastic element here, figured out by the number 4. And the elastic element is not such a basic spring as drawn on the slide, but rather is another compliant mechanism which is here. And with this, we were able to apply a displacement So a force through the spring applied on the element, and using the basic equation of the material strength theory, we can relate the force that we apply to a strain. So we are able to calculate how much strain we apply, and we are also able to measure how much strain we collect from the Bragg grating system. And we get also a linear response. So the originality is not in the physics of this, because this is known for optical fibers, but the novelty is that we are now able to apply it to mechanisms. And secondly, we also tested the bending detection capability with conventional 3-point bending. So here, the glass structure is put on 2 pivots and we press in the middle. So first, here the fiber is on the top above the neutral axis, which means that this portion of the material is compressed. Then we flip the system, and now there is a mistake in the drawing. Normally it should be below the neutral axis. I know it's yeah. And the last test that we made is to use the mechanism that I briefly mentioned, where we have the cross pivot here, guiding in rotation this needle. And so we are just pushing on the needle. We measure the angular deviation from the scale. So we know again how much strain we apply to the mechanism. And we measure this strain with our optical fiber inserted in the cavities, guided by a waveguide, and finishing in a Bragg grating in our mechanism. And again, we have a linear relationship in between with positive strains and negative strains according to the configuration. And now, the future of this research is to try to revisit the endoscopic tools which are already existing to measure force in medical catheters. There are many variants. Michel has worked on this a couple of years ago already. But in all these mechanisms, the basic idea is that you have here in blue the core of a catheter of an instrument. This is the functional element for the medical purpose. And this is surrounded by 3 optical fibers. You see here the cross-section figure. Here you have the core of the medical instrument, and here you have the 3 fibers. So that you can measure 3 degrees of freedom of force applied to the fiber, compression and 2 bendings. But even in the bending of the instrument, each fiber individually is undergoing a pure traction or a compression. You have no bending of the optical fiber, even if you have bending of the instrument. And so you are limited. You are intrinsically limited in terms of resolution with the system, because the force that you apply to your instrument is converted into a normal stress. And what could be interesting is to convert the force that you observe into a bending stress. That's how usually you break a piece of wood. When you are asked to break a piece of wood, you don't try to break it by pulling on it. You put it on your knee and you create bending, because with the same amount of force, you get a much, much higher stress, bending stress in the structure. And so that will be the key for our future development. We will create bending stress by create off-center structures prompts to bend in 3D thanks to the shaping of 3D compliant mechanism. So that's it for the presentation I wanted to share with you. I guess it's now time for discussions and questions.
So thank you very much. There are questions.
Yes, it seems to be on. So yes, thank you for the nice talk, Pierre. I was just wondering, you did mention that thermal effect were not important at some stage in glass, but then when you use fiber Bragg sensors, you know that you have coupling between strain measurements and temperature measurements. So I was wondering how you use that and you exploit that on the one hand, and why on the other hand you said thermal effect were negligible.
You're right. I mentioned the thermal effect or the absence of thermal effect. I mentioned the absence of thermal expansion, I think, or I wanted to say. So mechanically, there is a more limited effect of temperature or structures. But no, from the photonic point of view, you're completely right, of course. Temperature has the effect to expand the Bragg grating. This is an effect which is moderated, but it's not the most important effect on the Bragg gratings. The most important effect on the Bragg gratings is the variation here of the photonic coefficients of the Bragg grating system due to temperature. So we have also to compensate, to compensate the temperature, and so we are considering using a well-known system with a comparison fiber or a comparison portion of mechanism not submitted to the mechanical force to know how we have to correct the measure. But you're right, of course. Sorry for the confusion.
Other questions? Okay, thank you.
I have actually a comment because it was in the first part of the presentation. It was very nice to see those deformable structures, and actually this makes the pair with the presentation we had some weeks ago, where we had one of the fellows of BrIAS that was working on deformable structure using a textile that had different. That have different characteristics in the various directions. It's kind of quite interesting to see it in small, in a much smaller scale. And there was one thing that I discussed a lot with our fellow, that was Leonardo. It's the fact that there is always a trade-off between applying forces and applying movements, that it's much more a pressing problem than what it is in rigid robotics. Have you ever worked on something similar?
Yes, because I have a background of mechanical engineer. Of course, we know that to characterize an actuator is not enough to have neither the blocking force or the free elongation. We are interested in all the force displacement characteristics. And usually when I cannot create the smart polymers by myself, so that's why I'm associated to polymeric specialists in other universities. But what I realize is that in the community of chemistry and polymers, usually they are giving the free elongation. So they are putting their polymeric samples under the stimulus, and they are measuring how much contraction or how much motion they have. But of course, this corresponds to what I call the free elongation of the system. If you constrain the system by a force, you will indeed get less motion out of it. So this is to be characterized, but the scientific or technical challenge for this is to be able to characterize the force displacement curve of a very soft piece of material, because the Young modulus of these hydrogels, this is a few kPa, so this is much lower as what we have the habitude to measure. And moreover, the size of the voxel is extremely low. So you need to measure extremely small force with a lot of positioning accuracy. So it's more looking like atomic force microscopy characterization that people know in surface science than using the conventional equipment of the mechanical engineers. But we are working on this question.
Okay. So there is a question there. I'll arrive at the microphone.
Thank you. A question from the material scientist. I'm a chemist. The first part of your talk was more interesting to me, where you explained the hydrogels. My question is, hydrogels are used for soft robots, but of course there are some limitations because you need to involve some water for hydrogels. So how do you see from the application point of view, there are limitations for hydrogel-based soft robots, and the integration of these hydrogels to other soft material is also a kind of a challenge, apparently. So how do you see the perspective on this from your side?
So the first point is that we don't want to create full tools or full mechanisms. We are targeting functional extremity of endoscopic tools, so at a smaller scale. And in endoscopy, usually the physician have access to vision thanks to a very small camera embedded on the catheter. And from time to time, they need to clean the lens of this camera and they already flush water. So in the context in which we want to apply this, we could imagine that we continuously bring a lid. We don't need to flush the hydrogel, but we could imagine continuously bringing some liquid content or water content to keep the hydrogel in the working condition. My colleague in the polymer, but I cannot tell you the details because I don't know, I don't understand them, but are trying to use a less volatile solvent so that at least we could live for a duration of the operation without adding additional liquid. And also the environment is important because the hydrogel that we target, the cube that we target, are intended to be used in a warm, humid environment of the body. And so it's not a dry air submitted to air convection, promoting the evaporation of the water. But that's, of course, one of the key difficulties that we will have to address. And also on the non-volatile solvent or the non-drainable solvent, because it's a bit the same aspects. It's not only the evaporation, but also the viscosity of the solvent itself has an impact and that's why we are limited to small voxels actually, because our initial hydrogels were much too fluids, and so when we started to polymerize the bottom layer in contact with the glass slide on which the hydrogel cubes are printed, after a couple of layers, these parts were already polymerized, and so they were already behaving as the hydrogel. And instead of sucking the water, they were sucking the non-polymerized hydrogel, creating stresses in the structure that we already printed, leading to the detachment of the cubes. But now we have solved this issue, and we are able to print up to 300-400 micrometers cubes.
Okay, so with this, I would like to thank again Pierre for the very nice presentation and really for being with us today. So I would propose before the next two speakers to have a pause for a well-deserved coffee and of course to tempest Pierre with questions, curiosities and whatever else you have in your mind. Have a nice pause, a nice coffee, and see you soon. Okay, so welcome back. So we had a slightly longer pause than foreseen, mainly because, as foreseen, several of in the people in the room come to Pierre to make a lot of questions, and the discussion was so interesting that I had to interrupt them. Please forgive me. But we go on with our program for today, and it's my pleasure to introduce our next speaker, who's one of our junior fellows from Vietnam, and will speak to us about UAV in agriculture. It's a pity you couldn't be here on the workshop specialized in agriculture, but it will be a pleasure to hear to what you have to tell us.
Hello everyone, my name is Hieu. I come from Vietnam and I am very happy to stay here to introduce about our project about UAV and agriculture in Vietnam. At first, because I come from an Asian country and my country is still in the developing country and the agriculture is still one of our main products. So I want to introduce a little bit about my country and the rice field distribution. So in my country, the rice field distribution mostly is located in here and high in this area. And the Mekong Delta in Vietnam also raise about 56% of paddy field size on my country. However, during the time the rice cultivation area decreased per year. So we use a new technology is important to increase the productivity under the decrease of the rice cultivation area. And the rice field related to the farmers. And in Vietnam, the farmers are divided into two groups. The first group is modern farmers. They can use the vehicles. So we have the vehicles in here and in here. However, some farmers are still using traditional methods. They sowing by their hands and they also burn the field. In the end of every crop seasons, the farmers will burn the field to prepare for the next crop seasons. And this is about the farmers. Let's talk a little bit about the UAV in Vietnam. In here, the UAV in Vietnam start in around 2020. At first, the farmers use the UAVs, then they hire from the companies to make the pesticides. Almost 99% right now is still for the pesticides. So in 2023, the government decided to improve using drones as the first step to boosting the high techniques in farming. So that's the reason why we have a project about UAV and drones. And in case of the rice fields, actually the rice plant can divide it into three stages of the growth. First is the vegetative, the reproduction, and the ripening. Most problems come from this area, this time. And almost all the research right now in Vietnam is we supported in this area because of some problems. And today I will present you one of the most problems. This is my photo from the UAV taken 20 days after sowing. We can see in here is the high density in here, and some areas is low density. So after 20 or 30 days, the farmers will replant from the high density to the low density, and at this time the production will reduce. There are various reasons for this, and under my research we have problems. At first, it's about we can see in this photo the water level is the same, but actually this rice plant is better than this, and this is the worst. There are various reasons for this, but we can see the same water level. We can see the different water depth in here, and the water depth affect directly to the rice plant. And due to the different water depth, we can know that the roughness surface field is differently in here. So that's the reason I begin to research, I will introduce a method to evaluate the surface roughness. At first, I will introduce a method to evaluate the surface roughness. And then secondly, I will introduce how the surface roughness affected to the grass rough at the end of the crop seasons. So right now I will start. At first, I want to introduce my equipment. This is one UAV with the two cameras. First is the camera from the UAV, and the second the camera from the central company. This is a company from the US. And the observation area or the research area is in the reservoir. It's about 5 hectare field. It's a 5 hectare size, and this is the experimental field in my university. This area is only for research, so the surface roughness changes every time. So this area has a fully updike, the irrigation system, and it's also next to the river, so the water can flow in and flow out very easily. And the surface roughness changes every crop season due to other researchers or other uses. And you can see this is the photo of this area. And I took the fly, it's about 5 hectare, and the fly path is about 30 meter altitude with the speed is around 4 to 5 meter per second. And I take with this area the photos around 400 successive photos. So to build the photo of this area, I use a software so we can have 2 photo placed on the right side of the photo. On the top, this is RGB photo, and this is the spectral photo. And the RGB photo always affected by the sun glitter to here. So I mostly use this kind of photo to evaluate. This is the spectral photo, and from here we use the hydraulic tester analysis. And we can see in here the color. From this color we can see the distribution of the texture. And from this texture we can know some problems in here. I will discuss about this area later. But so we can see in here, and we can have some problems in here because the size of the photo is very large. So I make a small photos. We can see this is a problem on the field. This is on highland, and we can see this is the distribution look like this, and this is the RGB photo to test. So from here we have the spectral photo, and we have the digital photo, and the bit of the photo is from 0 to 255. So from this we can separate it into the groups. First, we can separate it into the surface roughness and the border and the terrain and the weather conditions. So after we label this from the surface roughness, we can label it to lowland, highland, or the normal land. And the border and terrain we can label it into the dike, the waterway, and the trees. And in weather conditions, it's almost a normal photo and flooded. So after we distribute, so we can see in here, I want to introduce a little bit about it in here. Because we can see this is a group of a lowland, very lowland area. I don't know why. At first, when I start this experiment, I don't know why. But for times I understand that because the riverside is in here, so the water will flow direct to here. But however, the size is too big. It's about 5 hectares. So if we have a very small area in here, it cannot fast remove the water out. So there will be a drainage system in here. In the normal day, it will look like this. We cannot divide, we cannot see by eyes. But after a heavy rain, which occurs usually in my country, the surface look like this, and it will affect directly to the rice field in here. This is the way I introduce you about the surface roughness of how to evaluate the surface roughness. Okay, next I will introduce you about how the surface roughness affect to the agronomy and to the crop yields. And this project is based on the Japan JICA government sponsor. This project start from 2023, and right now it is continuous. It will be end in the next year in 2025. I am a part of this project, and this project we have first we have a landlord. This is a very important person. He's a landlord, and the second we have a semi-autonomous tractor because it's a semi-autonomous because when the tractor rotates on the rice field, we also need agricultural engineering to do this because on the rice field many problems can occur. And this is my UAV. And the purpose of this project is that we apply a new techniques and we give advice to the farmers and finally we try to increase the grain yield of this area. And this is also his field, but we make experimental in here. And this project we can include first we prepare the scrub season preparation. Don't like the farmer they burn the season, they burn the field. We make some, I don't know how to say. We prepare, and after that we use the germination by using the sowing machine. This machine comes from the project. And after that we also evaluate the methane emission. And we finally we harvest. And I work in this project. This is the experimental field of this project. And this is the car, and this is 2 hectare experimental field. And this is next to the, you can see this is next to the road. And this is mostly, in this area, is mostly about the rice field. So we make the experimental in here so the farmers in here can see very easily what we do. So we can give an advice for them. And next this is the RGB photo, and this is the spectral photo. And as the previous research, we also focus on the experimental field. And this is the experimental field, and after we use the Harley tester, we can see there is a similar some dikes in here, and this is a very good distribution. We can see some dike in here. So in here I suggested to take a samples, rice sample. So to the end of the crop season, we can collect some rice plants to evaluate the agronomic traits in here. So this I mainly focus on 3 areas. This is A, B, and C. After that, we put the 3 square like this. This size is a 50 plus 50 size square. And so we can see this is the rice plant after sowing machine. It's a very good distribution. So the A, B, and C look like this. So if we see in this photo, we can see that the surface roughness is quite differently from here and here and to here. And this area, they also take an experiment. They also take some agronomic, evaluate the agronomic trails in here. But this is not important because this area and this area is similar the same. So to make it sure we evaluate, it's about, this area is about 45 meter and 30 meter to here. And this area is about 20 to 22 meters. And the C is around 155 meter in here. And this is my mission. And to the end of the project is on the harvest day. Let's take a look on the harvest day. This is position C. You can see this is green and this is yellow. And the farmers don't understand why. This is green and this is yellow. And this is a problem because it will reduce the crop yield, the production. In here it is already yellow. And in here when we can see on the area it's quite yellow, but so it is very difficult to compare. So we use you see it's already yellow. So we use the normalized distribution, the NDVI, the normalized distribution vegetation index to evaluate the spectrum. Let's take a look. This is position. Let's first talk about the position B, because this is, you see, it's distributed very good. In here, the normalized distribution around 0.1. That means that the drop the BrIAS plant in here is they don't photosynthesis. They're already yellow on, so we don't. It's already ready for harvest. But in here, we can see it's a very strong photosynthesis in here, and in here is nothing. So the distribution is differently. And in A, the situation is very similar with C. Here, this is still photosynthesis in some problems in here, but in here it's mostly very strong, effective. And we take about the agronomic trait. So in the agronomic trait, at B, the plant's height is smallest, the particle length is smallest, but the number of particle length is very high. And this is the high range yield. And this is very near, this value is very near to the total grand yield of this paddy field on when we finish to harvest. And in C, we can see the plant height is very high, but the number of particles is very small. We can see it. And the B is quite near. A is quite near B, but the grand yield is small. So the B is the highest value, and is the nearest value to the total of the rice field. There are some reasons for this. At first, this is the output of the system drainage. All the nutrition come from here will be flow to here. So there are too much nutrition. When it got too much nutrition, the rice plant is got too much nutrition. It's become tall, green. It's photosynthesis strongly, and the rice ribbon become light. And this is the normal land. So with the normal land, we got a very high crop yields. And in here, this is a highland. That's the roots cannot get enough the water from the nutrient from the drylands, cannot produce well. So from here we suggested to first to change the method for preparing the soil condition in this area, preparing the soil condition before every crop season. And I suggest to change the blowing device on the tractors, which means that we make a different way to prepare the land, the soil. Here is the season next to the first season, the crop season. We can see that the normal distribution is differently. That means that they change the way the device on the tractor to prepare the soil in here. So in the next season, we can see the distribution is very good. So in this crop season, we got the second of production during 20 years of the history in this district. This is a very good achievement. So actually the program is still continuous working, but because I don't have enough time to introduce, so I will talk a little bit about our achievement in this part. At first, we can explain how the surface roughness affected to the rice plant. So this is very important because we can suggest to the farmers, and the farmers, when they believe you, you have to get a good relationship with the farmers, so they change the way to make the land. Secondly, we reduce the rice germination from over 11 kilogram per hectare to 9 kilogram per hectare. And when we reduce it, the farmer on the district begin following up our suggestions. And we also get the second highest ranking yield production in 30 years in the summer fall season. That means this is in this season. That's all about my introduction. Thank you for your attention.
Are there questions?
I have a question concerning the first part of your talk on the measurement of the water depth which is the measure basically of the roughness of the ground below the water level. So how fast does this surface roughness change? Does it vary from time to time, from day to day, from year to year?
Yeah, this is an interesting question. Actually, the surface roughness will change after the farmers burn the field. Mostly after the farmer burn the field, because they burn the field to prepare for the next crop season, and this time is very important. This time is very important. So we suggested them not to burn the field. It emits a lot of CO2. So we suggest them to use chemical. So we suggest them to use the chemical. And after this time, we will know about the surface roughness. After the chemical emission, it should be 20 days. And after that, we will see the surface roughness. And after that, we will suggest what to do in here at that time. It's a very important time because the time is very strict. And the farmers will following the requested from the suggestion from the government. So this time is very strict. We have to do fast. So that's the reason why I have to prepare the method to evaluate the surface roughness very fast, very early. So this is very important time. From here to here is about 20 days. Yeah. So when the surface roughness and we use the tractors, and the rice fields will look like this. And after that, when the rice plant becomes tall, they will not change.
Other questions?
Okay. So I thank you for your presentation. Does it work? Okay. Thank you for the presentation. Actually, I have one question that is, how often were you collecting data? So how often were you flying during this? During the operations, and which kind of cameras you had on board? You said it, but probably I kind of missed.
I will introduce you more clearly because I prepare another slide. But okay, I will talk very fast. Okay, yeah. And okay, no, sorry. We fly at first after the first time we fly is in before we sowing. That means 20 minutes before we sowing. At the first time when we take the experimental, we fly before sowing 20 minutes. But when in the second time, because it's experimental, and in the second time we fly several days before that. We fly 2 weeks before the. On this day, you can see the color is differently because due to the tractors, and we fly to evaluate the surface roughness 2 weeks before they sowing. And on the day they make a sowing, we fly again. Mm-hmm. And this is the first time. And after that, we fly the second time to understand the height of the rice plant. It look like this. It's 15 days after sowing.
Okay, so you have 4 or 5 flights per season for each field.
Yeah, we fly in the same field.
Okay.
This is 15 days after sowing because we want, this is another project, but we want to understand is it good or not to get height. We can see in here it's very good. And after that we fly. My mission is we fly on the harvest day because I need to understand about the spectrum, the normalized distribution vegetation index in here. So it's normally about 3 to 4 flight time. Okay. Depends on the mission.
And each flight probably you cover 2 or 3 hectares more or less, I imagine.
Sorry?
each flight you can cover 2 or 3 hectares for the speeds I've seen.
Oh yeah, this is a big problem because it depends on the battery.
Okay.
This normally is a 2 hectare, and you know this device. It costs 20 minutes to fly in this area, and we use 2 battery. So everything must be done exactly because we don't have enough battery to fly many times.
And I have a last question for you. Do you think, because I imagine that rice in terms of economical production is not much. I imagine it's less than $1,000 per hectare as total income at the end. Do you think from the economical viewpoint how we can make this kind of methodology sustainable?
Oh yeah, it should be.
Okay.
We increase the total for the farmers, and he smile very happy, and that's important to me.
Okay, I don't have other questions. I don't know if someone else in the speakers have, the public has. It seems so.
Thank you for that presentation. My question is, in a way, a follow-up from the first question. You presented the slide where you showed water depth, and that slide. And so, what is the difference in water depth from the, well, I guess on the far right it looks like it's 0, versus the far left. Like how big of a difference is that depth? Is it an inch or 2? Is it?
So we can see again in here. This is about the roughness. This is the, we can have A, B, and C. So we can see in C, this is the deepest, and the grain becomes, you can see in here, this is still green. That means this is not good the time for harvest, because there is a reason is that because this is too much nutrition in here. So it's become green. We can see in the photo in here, carefully we can see it's a bigger size than here, and it's a bigger size than here, because the nutrition in here is too much. And the problem in here, you can see the size is smaller because the roots in here didn't got enough water and didn't got enough nutrients. I love this photo very much because they can, you can see the size of the rice plant is differently. So.
Yeah, I think I understand that, but I'm curious, like how much water are we talking about? Are we talking about, again, a few centimeters of water? Are we talking about,
the surface? Yeah, because the roughness is differently, so we can see it here, it's still green and it's yellow. So I suggest the farmers, they make this area again. They prepare the area again. So this at this time the agronomic trace it will be better. For example, we can see it's in C. Although the rice plant is very high, but the grain yield is very small. So it's affect directly to the grain yield.
Okay. Now this part of the question is connected in my brain. It may not be in yours. How long can you leave rice plants that are in B in this case? How long can you leave them in the soil water before you have to remove them? Can you wait for the other areas to move closer to being?
I understand.
Or is that an unrealistic plan?
That's another question. I want to show you this area. Here, on this area, not my experimental. I mean, on the district, they will they will make the sowing at the same time, and they will do collect at the same time. This is requested from the government. Because the government asks we to do at the same time. They don't. The problem, the most dangerous problem is about the mouse. If we collect early, the mouse will move from here to somewhere. And if we cannot collect at the same time, the late, we got a lot of mouse, and they will eat on the rice plant of this area. That's the very, we cannot control the problems. Thank you for your questions.
Okay. Is it working? Okay. So with this, I want to thank again you for the nice presentation. It was very interesting, also because it's a kind of crop we are not so used to in Europe, or at least we use much less than in Asia, and it's quite kind of interesting to see as one thing that we always repeat, that for each single crop in precision agriculture there are different problems. So thank you again, and I'm sure we will have a lot to chat in the next few weeks that you are with us. And I want to pass now to our last speaker. So in the while that they are doing the technical change, some introduction. So we had a professor of ULB in the first as a first speaker. Now we had one junior fellow of BrIAS. Our last speaker is a PhD student from this department that will present on yet a different subject that is concerning robotics for rehabilitation. And very often when one thinks about robotics for rehabilitation, thinks about actuated robots. But in this case, as Robin will show us, there was all a journey to arrive to the conclusion that the first thing that we needed to do was to create a measurement instrument, and he will show something on how to arrive to that. So as soon as the technical part is done, it will be my pleasure to leave the stage to Robin. Are you ready?
I think so, yes.
You need a microphone if you want to be ready.
Yes, thank you.
And I leave you the stage.
Okay, I think everything's fine on the technical points. So, as Emmanuel said, I'm Robin Wilmar. I'm a PhD student, and is it working? Okay. And my thesis is about the design of a 6 degree of freedom kinematics measurement tool, which has the aim to improve knee rehabilitation. And today I'd like to talk about, that's the reason why today I'd like to talk about robotics and what robotics brings to knee rehabilitation. And since it's the nature of this topic is multidisciplinary, I'd like to give a few words of context about healthcare, but also about why my research has been oriented towards robotics and why in particular for the knee. So let's start first with the healthcare context. I'm sure you know that there is a shortage of physiotherapists in Europe. A recent communication of the World Health Organization, actually the European Office of World Health Organization, warned that 394 million of people, so it's almost the half of the European community, need rehabilitation care because they are suffering for health condition, but they don't have access to that care because of the shortage of physiotherapists. And that crisis, if we can say that, is so critical that in 2023, physiotherapy was added to Europe's shortage occupation list to acknowledge the fact that there is a disparity between the need and the delivery of physiotherapy care. So in response to that crisis, the main solution is to promote the development of adequate and well-trained multidisciplinary rehabilitation staff. So we have to form more physiotherapists. But what if it's not enough to form more physiotherapists? And what do we do in the transition while we still need a lot of physiotherapists? Well, another solution is to increase the number of patients by physiotherapists in the same amount of working hours, because we don't want to increase their working hours. It would be detrimental for their health. It's not sustainable in one end, and on the other end, increasing the number of working hours for the physiotherapists would lead to work-related pathologies, to an increase of work-related pathologies also. So some scientists, by noticing that in some aspects of the physiotherapist's work are quite repetitive, thought that that might be interesting to introduce robotics in that field. Why robotics? Because robotics has one ability, the ability to repeat several movements quite precisely and without knowing fatigue or boredom. And actually, it's a quite complex problem, because we might think naively that to allow the physiotherapists to have more patients, we could just build another humanoid robot that does the gesture of the physiotherapist. And if we have such a machine, we could imagine that the physiotherapist supervise the robots while he's having a lot of patients in the same time, instead of one for just one rehabilitation appointment. But it's a little bit optimistic to think like that, because the complexity of the human body is really high. So we will not be able to do a humanoid robot that will be able to make physiotherapy tomorrow. So to reduce the complexity of the problem, we can decide to focus on specific anatomical joints. And that's what robotics in rehabilitation has done. And so why did I focus more my research on knee? It's because the knee is one of the most damaged joints in the population. And so if we can provide a knee rehabilitation device that will be able to give a consistent rehabilitation procedure, this might benefit to the greatest number of people. In fact, this is not a new topic, because robotics in physiotherapy dates back to 1975, with the first machine being the pointer. No. This one, okay. With the first machine being this one, so CPM for continuous passive motion. It's a machine in which the patient puts his leg, and then you have the machine that presses over the foot, and it's used in after surgery of total knee surgery, for example, to recover. In fact, it's directly after the operation to recover a great amplitude of motion on the knee flexion extension. But if we use that machine to do re-education in a physiotherapy office, well, research proved that it's not effective at all, and some patients might complain because for this machine, some assumptions are made that makes the design of this machine not proper to the knee joint. After that machine, other attempts were made with gait trainers, therapeutic machines, exoskeletons also are solutions that were thought about to improve knee rehabilitation. But again, if we look at all these machines, there is just 1 degree of freedom. So you can just bend the machine over one axis. Same here, and here, well, the knee at least is not constrained. You can apply a force. But also there are some patients complaining about those machines because they feel discomfort when using them. If they have the advantage to exist, these machines, as I said, make a lot of oversimplistic assumptions. And also, we are in the right to ask one question: which rehabilitation protocol will we apply with those machines? Well, when I ask myself this question, I've been a little bit disturbed by the answer to that question, because in fact, it's really difficult to choose which rehabilitation protocol you will apply with the machine, because when we are evaluating different protocol for the moment, there are a lot of bias in the studies. It's usually based on patient feedback. We mainly rely on trust that the patient has done the exercises at home, and also we don't know if the patient has correctly done the exercises at home. So it would be interesting to be able to monitor those exercises. So as long as physiotherapists do not have the right tools to quantify the patient's progress, it's impossible for us to evaluate the success of one rehabilitation protocol with respect to another. And the physiotherapists with whom I spoke to were not really interested by the idea of us developing a machine to do the rehabilitation, but were more interested by the tools that we can provide them to measure the knee kinematics. And so, I said multiple times, we are interested in measuring the knee kinematics. I think it's a good moment to introduce what I mean by measuring knee kinematics. So, what is kinematics and what do we mean by the knee? When we look at the knee, we see that it's made of 4 bones. Some researchers consider that it's made only of 3 bones. So we have the femur, the tibia, and the patella here, the small ovoid bone that is here. And we have the 4th one that is not always considered as a part of the joint, the fibula, which is here. So if we have 3 bones in the joint, it means that we have a two-joint articulation. An articulation between the tibia and the femur, which is the tibiofemoral joint, and an articulation between the femur and the patella, which is the patellofemoral joint. So, to simplify, in the rest of the presentation, I will talk about the knee joint, but in fact, I'm always talking about the tibiofemoral joint, because I'm interested in knowing what's the movement of the tibia with respect to the femur. So, what are the tools that are used to measure these kinematics? For the moment, in the physiotherapist's office, it's just one goniometer. But if we look here at the knee complex, we see that when we are bending the knee, of course, the main motion of the knee is flexion extension, but it's not just 1 degree of freedom. When you bend the knee, you probably think that it's you bend the knee as you would make a door rotate around its axis, but there is not only a rotation motion. When you bend, when you are in flexion extension, you also have some gliding of the tibia on plateau on the condyles of the femur. So a posterior motion combined with a distal motion. So we've seen that we already need three degrees of freedom to describe the motion of the tibia with respect to the one of the femur. But we also have other translations, so the medial-lateral translation, and it's possible to internally or externally rotate the tibia, and also you have, in some cases, a little bit of varus valgus or adduction-abduction in the knee. So we need, in fact, 6 degrees of freedom to describe the motion of the tibia with respect to the femur. And for the moment, in the physiotherapist's office, we only have a 1 degree goniometer. Luckily, in the scientific literature, you have other methods to more accurately describe the motion of the tibia with respect to the femur. So there are electrical linkage methods. That's the one I chose to use in my thesis to develop a measuring tool, and I explain later why I chose this one. So here you can see one picture of example of those devices. In fact, you have one part of the device that is attached to the thigh, the other one to the calf, and in between there are several rigid bodies that move with respect to one another, and based on the movement of each bodies, you can reconstruct the position of the tibia with respect to the one of the femur. With the radiographic techniques, we are using, well, RX radio to measure the movement. So we make several photos of the bone, and then by putting some markers, we are able to reconstruct the movement over the time. We can even now reconstruct it in 3D, but that technique is not really healthy for the patient because he receives X-rays while performing these tests. Another interesting method is the video technique. So, like in camera motion, you can put some markers on the thighs and the calf of the patient and measure how it moves on the time. There are other techniques here like electromagnetic device and sound-based systems, which works with the emitters and receptors to locate the position of one rigid body, so the femur, with respect to the other one, the tibia. But there are quite old techniques that showed their limitations in comparison with the electrical linkage methods and the video techniques. So electrical linkage methods and video techniques have both a disadvantage. This disadvantage lies on the fact that you have to stick some sensor, some light reflector on the soft tissue of the leg. And since they are soft, you might have some noise on the position of the femur, because what you are actually measuring is the position of the skin. And when you are moving your leg, in fact, you are also moving your skin. And that's the same problem with the electrical linkage methods, because you have attachments that are placed around the thigh and the calf, and you have the same problem because you have what we call migration of the attachments. So here is a 6 degree of freedom electrical spatial linkage that I propose in my thesis. You have 6 different, you have one rigid body that is attached to the thigh, the last one of the kinematic chain, so an assembly of different rigid body that is connected to the calf, and in between you have 1, 2, 3, 4, 5 other rigid bodies. And with that, I can measure all different angles, or here linear displacement. And thanks to that data, I will be able to reconstruct the 6 degrees of freedom of the kinematics of the knee. Why did I choose that solution instead of video solution, which are also promising features? Well, you have to know that video techniques are used in to study the gait, so in laboratories, and they require big infrastructure. And for me, it's not conceivable to think that physiotherapists would have such big infrastructure in their office. So if we could provide a smaller infrastructure to the physiotherapists, this one can be used in an office. It can even be taken at home, and so the patient can use it, and you will have the possibility to monitor if the patient is doing correctly the exercises. It's lightweight, and there is a possible evolution towards actuation of the device if we want to do active rehabilitation after studying which methods of which protocol of rehabilitation is better and should be applied for recovering faster. So the challenges we faced for developing such a device is that it must be usable on both legs, it must be lightweight, and must not restrict the patient during its motion, and we must reduce the migration of the attachments. So as I said, here you see the different, you see the kinematic chain, in fact, of the device, and we see that it's 1, 2, 3 rotation, followed by a prismatic rotation, so it moves linearly, and then again 2 other rotations. This special configuration was provided by the literature, the scientific literature. Actually, the best one that reduces the attachment migration is 6 prismatic, but technologically it's difficult to put in place, and also the material used to make such joints is quite heavy. So a good alternative is the one that we use to reduce the weight. It's also a solution to ease the use of the device on both legs, because we only have to turn around some axis to make it adaptable to the left or the right leg. And it allows to avoid attachment or to reduce attachment migration because of this special configuration that reduce the constraints that are put on the attachment. To not restrict, to respect the fact that we don't have to restrict the movements of the patient, we decided to transmit the data of all the sensors by Bluetooth to a graphical user interface. And we also thought of 2 ways to reduce the migration of the attachment, which are the localization of the attachment of the tibia on the tibial crease, and also we glued in some way the leg with the attachment to the leg with gel pads. Just for the anecdote, there are some studies that attempt to screw directly on the patient the device, such devices, in the bone to study the migration and to see if it would not be better to have better results. Actually, it's rigidly attached, so that's a good thing. But the problem is that by doing that, you are inserting pins in between the muscles, and so you have the problem that you are restricting the patient's movements. So for the data process, we have, as I said, 5 rotary incremental encoders and 1 linear incremental encoder, so to measure the rotation and to measure the linear displacement. This is sent to a control processing unit, and that unit sends the data through Bluetooth to a graphical user interface. In that graphical user interface, the raw data of the encoders is processed. In fact, we applied what we call in robotics homogeneous transformation matrix to pass from one frame to a clinical frame that is based on the Grand and Sante representation, for those who knows him or his work. And that's how we can extract from the 6 degrees of freedom that are measured with the device the clinical data, so the 3 translation and the 3 rotation of the knee. Here is a video of the device, such that you understand better maybe how it works. So you have a real-time visualization of the tibia moving around the femur. Here is your graphical interface, where you have the possibility to calibrate the encoders, to render the data from the sensors, those clinical data. And then one aspect that is quite interesting for the physiotherapist is that you have a small learning time that you can with the device. You still have to enter 2 measures manually correctly and to get 2 epicondyles of the femur. But one important aspect of this prototype is that we are able to measure the translation, the clinical translation, which was not the case before. Sorry. Maybe I. Okay. it's fine. And to finish my presentation, because the BrIAS main topic this year was robotics for sustainability, I wanted to apply as an exercise for me that the requirements of sustainability for the Europe. And there are three aspects that I can highlight in my work. First, one of objective of the Europe for sustainability is to have a healthy population, and by developing solution to have a healthy population, we enter in the sustainability program. Also, 80% of our parts are 3D printed and are made with PLA, which is a plastic made of vegetal material, so corn, for example. And so this is the ecological aspect of the project, because this plastic can be recycled. And on a social point of view, because these parts can be printed, it means that they can also be printed in countries where there are less infrastructures. And I think it's a good thing to think about that. And honestly, I did not integrate all those things from the very beginning of the research, but that's the trend in engineering that we see more and more, to try to think of we are creating something and then this thing will have end life, and so we have to think of how it will be recycled and so on. Thank you for listening to me.
Are there questions?
Hi. So thanks a lot for a very nice, very clear presentation. I thought also you're very honest when talking about the introduction of technology that can potentially replace human labor. I heard only last week, accounts that were way more optimistic. The fact that there is a lack of healthcare professionals does not mean that introducing robots will solve the problem. In fact, you can scare them away as well.
Exactly.
So, however, I want you to elaborate a bit on this, because you said first that the physiotherapists did not want a tool that could replace their labor, but more understanding the kinematic of the knee. Mm-hmm. And then, is that what you went for, or are still hoping to have this combination? And if so, how do you see this human-computer interaction in some way?
That's where I went for. So we decided to change completely the direction of my thesis, which was to make an actuated robotic device for knee rehabilitation, and instead developing a measuring tool. And with that, a measuring tool that is affordable by the physiotherapists, that can be easily used in his office, such that, in fact, he can proceed to some control. Just one example, when the patients have injury of cruciate ligaments, one typical test a physiotherapist do is that he's blocking the leg, the femur, the thigh, and then he's the knee is bent because the patient is seated, and then he pulls on the knee, and then he's assessing the drawer, because since you have an injury in the ligaments, the joint, the knee joint is not stable, might not be stable anymore, and so normally if I pull on your knee, it should not move. But here you have what we call a drawer, so horizontal displacement of the tibia, with respect to the femur. And is assessing quantitatively, okay, I think that it's 2 millimeters of drawer, or 5 millimeters, knowing that at above 5 millimeters of drawer, you will have to make a surgery. And if we provide some tools like the one I propose here, they would be able to put it on the patient, make that test, for example, and retrieve the data and see, okay, that's a drawer of 2.5 millimeter, that's a drawer of 6 millimeter, and
so you gave up on the first part completely, correct?
yes.
Okay.
Well,
or you hope to still...
Yes. Just to complete my answer, it's not that we are still in the topic of rehabilitation, because, but not of active rehabilitation, because we can also propose some exercises to the patient that he can do at home and that are monitored with the device and could give him some feedback. You are doing wrong the exercise, or try to not to push too much on your articulation. I don't know, but this has to be thought.
Thank you for your presentation. It's a very, very intriguing idea. As a physical therapist, I've got some pragmatic questions for you.
Okay.
What we know is anytime we put something on somebody, it changes the way they move. For example, or do something with somebody. For example, what we share with our students, that it takes 45 minutes of treadmill walking to approximate gait over ground.
Yeah.
So how long do you think it takes to use a device like this to approximate real or biological movement? And then I've got some questions about error.
That's a good question, and I think that we should make a study about that. My feeling, because I wear it, some of my colleagues wore it to just to test it, but not in a serious way, because we still need to make tests with a certain protocol to assess the repeatability of the measures and so on. But from the feedback they gave us and the feedback that I have, it's quite lightweight. So at the beginning, it's a little bit disturbing more to have the attachment. And before putting the gel pads to the attachment, we had some migration that was also disturbing while walking. But with the gel pads, you don't need to strengthen that much the attachment, so it's also reduced the impact of the device on your gait or on your movements. But I think also that is relevant for gait analysis, because in gait analysis you will have some movement to perform if you are more static, and that the physiotherapist asks to make some squat or some other exercises which purpose is to re-educate the knee. Since you don't have this velocity of the body, the inertia, I think you feel it less also.
Okay, great. So I think that we believe that the most precise device to measure joint movement is the digital inclinometer, right? So it's a digital device that goes on the limb. You move it through a range of motion. You can measure, how far the joint is moving in terms of range. But we have also an understanding that the technique of measuring joint range of motion probably has between a 5 to 10 degree error rate. Mm-hmm. Are you going to be able to produce a similar number in terms of like what variability are you seeing in your measurement?
I'd like to have an error of 1 or 2 degrees on the device. That's what you were asking for, right?
Yeah, I understand. Okay, there's the error of the device.
Yes.
Right? And then there's the error of actually measuring range in a biological species, right? And so, for example, the range of motion of our knee changes throughout the day.
Okay.
Right? So when you wake up in the morning and you measure range of motion, it's probably less than after you've been out walking and moving around.
Yes.
And I think that's in terms of when you think about applying something clinically, I think you have to balance the accuracy, the cost, the pragmatic application of a device.
You mean taking into account all these aspects, the fact that depending on the part of the day, you will have different results on one patient, or?
Yeah, I just think whatever measurement tool you use, it has to be more precise than what a human can do with the devices they already have access to.
Yeah, exactly.
In order for it to be to be used significantly in the clinic.
Yes, but this will be more accurate.
But it could be more accurate, right? Mechanically, right? I agree, 100% it's going to be more accurate.
Yes.
But there's going to be variation because of your interacting with a biological species. And the question is are you able to really improve the accuracy of that measurement? I guess that would be my challenging question.
I'm not sure I'm understanding the question, but do you mean by biological interaction, do you mean the placement of the attachment and the adaptivity of the device?
Well, okay, there's the placement of device, right?
Yes.
That has to have, and we have very specific guidelines. Like if we're going to measure knee range of motion, right? That you go to a textbook and there's a specific way to do it. It has to be done it can't be done in a sitting position. The patient needs to be supine. There's lots of detail-y things related to that. But there's that, right? There's the technique and the placement of the device, and then there's just the variability in the biological tissues.
Yes, but we don't try to have each time the same measurements from one patient to another, so we will be able to track the differences between different specimens. We will be able to also we have a procedure where we align the one axis of the device on the flexion extension axis, and based on that we also have a correction of the transformation of the raw data into consistent clinical data by detecting if we have a misalignment while placing the device on the patient, because you might have some error due to the placement also of the device by the physiotherapist. So we try to think about all these things while developing the device, and how we can correct eventual errors coming from human.
Sure. So okay, you right now you're limited to 60 degrees, right?
Right now I have the 6 degrees of freedom with me.
So normal knee flexion is between 130 and 145 degrees.
Yes.
Right, and so will you eventually be able to achieve that level?
That range of motion. Yes, because I think it's just when you are making a squat and a complete squat, so that device is able to track the flexion extension of the knee from fully extended to like this. So I think so, yes.
Okay, great, thanks.
I don't know if there are other questions. One little question, even if I'm part of the project, so I should remember these things.
Yes.
For how long the device can be used by a patient? So how long is the battery lasting at the moment?
It can last 1 day.
So you could take a complete one-day activity of one person in line of principle.
Yes, exactly. And also we thought about that. So you have a battery pack in the design, so you can remove the battery. You have a second battery in case you need to use your device more than expected. And yeah.
Okay, so I'd like to thank again Robin for his presentation. As per our tradition, we are late, as usual, which is always a good sign because it means that one, probably we don't take ourselves too seriously, and two, we always have a lot of questions at the end, and so we always run longer. With this last talk, we end here, let's say, the formal part of our Thursday's meetings. Of course, for all the present, you are more than welcome to stay over. There is coffee. This space, it's all for us. Feel free to basically to speak with whoever, to try to get idea, to try to come even with strange ideas, because strange ideas and crazy ideas are what make things progress. And for the people at home, sorry we cannot offer you coffee, but we hope to have you soon with us again. And with this, thank you for the afternoon, and see you next week.